is Biqi Wang. Biqi is currently working as a PhD candidate under Dr. Rolando Burgos at CPES, and she received her bachelor degree from Shanghai Jiao Tong University and her master from Ohio State University. Her research includes power electronics, systems modeling, power system black start, and power system stability analysis. And her talk will be a grid forming control scheme for inverter-based PV generation black start featuring grid regulation capabilities. Biqi, the floor is yours.
Okay. Thank you, Dr. Jin, for your introduction. The title of my today's presentation is a grid forming control scheme for inverter-based PV generation, black start featuring grid regulation capabilities. So this is the outline of my today's presentation. I'll start with background, then present the GFI featuring black start capability. It includes the consideration in the inverter control design and also present the proposed grid forming control. And then the simulation results of the whole black start process will be presented. And after that is concluding remarks. So blackouts in power system, although not often occur, can have serious consequences impacting critical infrastructure, public health, and economic activities. So our transmission operators are required to have plans and resources available to restore the grid following a partial or total shutdown. The definition of the black start is given here. It means the restarting generations without any external power, and we need to restore the power grid after blackout events. So here in this slide shows a typical black start sequence, which is defined by PJM. It includes some basic steps shown here. For example, first we need to have black start units to start it to form islands without any external sources. And also the cranking path for the next step should be energized. Usually it's transmission lines. And after that, simulation loads should be picked up. And also the non-black start units, we call it target generating resources. They should be restored. And one thing to notice is to initiate their electricity production, external power are usually required by their auxiliary equipment, such as motors and pumps. And finally, the islands should be synchronized to each other and interconnected to form the final complete grid. In modern transmission systems, the increasing energy share of inverter-based resources has largely changed the grid generation profile, and it makes the system-level dynamic behaviors much more complex. So the black start capability has become a crucial requirement for IBRs. In today's black start operation in US, they're almost exclusively carried out by traditional power plants that are interfacing grid through synchronized generator, including hydro, gas turbine, and nuclear plants. And among all these black start units registered with NERC, we have gas turbine about 60% and hydro takes up about 37. Well, to this day, the IBR in transmission system and DER in distribution system are still zero. And with the ongoing effort, integration of renewable energy resources, we see the US wind and solar generation capacity is predicted to hit a very high volume in 2026. And this introduced new opportunities associated with black start restoration. This table summarizes the key features of different power plants, which shows the advantages of operating renewable energy resources as black start units. They almost require 0% of auxiliary power and very short startup time. Besides, they offer a faster power ramping rate, which can speed up the grid restoration with rapid load pickup. And also grid-tied power electronic inverters can be controlled with great flexibility, allowing IBR respond faster under frequency and voltage excursion compared to SGs. usually within a few seconds. So despite all these advantages, they also present some key challenges. For example, the intermittency and the unpredictability of PV and wind plants tends to increase the chance of power imbalance, which is likely to cause a second blackout. Also, it is challenging to guarantee the small signal stability of grid-tie inverter with a series of switching actions in the black start process to change the grid conditions, which will also change the inverter operation point and the stability region. The small signal stability is especially critical during the initial phase of system restoration. The instability can be triggered more easily under a relatively weak grid. So a special case here is before the cranking of any other non-black start target generators. The combination of cranking paths and the loads on the grid side can be equivalent to a passive load or RL load, as shown in this DQ-friend average model of grid-tie inverter. So compared to the inverter interfacing a large grid that we are familiar with, we have much higher grid side impedance, tends to reduce the system stability margin. So we need to follow an updated control design principle. Also, the IBR inverter should be controlled to withstand different types of switching transients and maintain the grid side voltage and frequency. So we can't use the traditional PLL-based grid-following inverter in our case. However, the grid-forming inverter, it offers an alternative grid synchronization approach, and it is a promising choice in black star application. The synchronization mechanism of the virtual synchronized generator, it mimics the power balance of a real synchronized generator. And it will transfer any mismatch between the input and output power into a change in the rotating speed, and which in turn will reduce this mismatch as the famous equation of the swing equation shows. And operating GFI outside of the peak power mode, it allows the GFI to realize the grid side regulation based on PF and QV droop. So the GFI can alleviate the grid frequency and voltage deviation by adjusting the active power and reactive power it injects into the grid. For the next part is the grid forming inverter. So here shows an overview of the grid forming PV inverter. The PV area is interfaced with the grid through the inverter switching network, LCL filter, and step-up transformer. The GFI control scheme is shown here. So the power balance synchronization, it uses a frequency lock synchronization mechanism, and it will operating the inverter as a virtual synchronized generator. The IEEE 2000 compliant PF droop and QV droop were implemented, so the GSR can adjust its PNQ injection in response to grid condition variation. And the reactive power loop generates the virtual back EMF is cascaded with the inner current control loop via the virtual impedance loop. And as we mentioned before, the GFI controller should be carefully tuned and designed, especially under the very weak grid in the black star initial stage. This will involve stability consideration of the impacts from various control and system factors. And due to the time limitation, here we only present two important examples. One is the consideration of PBS, as shown by the equivalent circuit here. When the GFI is interconnected with passive load before a second generating unit is cranked, we can calculate delta, which is defined as the phase difference between virtual back EMF and PCC voltage using this equation shows here. And we see that under specified virtual impedance and load impedance, the delta value is fixed, which means P and Q are regulated together by the voltage regulator with fixed power factor. And the P regulation function of PBS is actually deactivated in the initial stage of black start. And in order to maintain a constant frequency, an integration term can be fed back to the power reference for isochronous mode operation. And after the non-black star generator is connected, this feedback should be disabled for realizing a Joule-based power sharing. And another consideration lies in the grid-side impedance. This figure shows the virtual impedance loop gain measured from passive load interconnected GFI average model under different grid impedance values. And we can see with a larger grid side impedance, which means a smaller system load, the VIL bandwidth increases, the stability margin tends to reduce. The VIL is very likely to go unstable under a very light load, especially under no load condition. So we suggest that the VIL should be enabled after the pickup of the first load along our cranking path. And in aid of that, we can use an AC voltage loop to establish the initial grid voltage. So based on all the consideration we presented, a black star friendly grid forming control is proposed here. One thing is at TVL, which is usually designed to occur after the pickup of the first load along the cranking path. We switch the current reference from being given by the voltage regulation loop to being given by the virtual impedance loop. And the grid forming control is enabled. And another time is at TPBS. It is designed prior to the introducing of a second IBR or synchronous generator. The integration feedback is cut off to enable the PF Joule control, and the inverter control will be out of the isochronous mode to the power Joule mode. And next, let's look at some simulation results. So this is the Black Star power system testbed we use is a 7-bus transmission system. It is designed based on real system data and simulated in a PISCAD platform to demonstrate a complete Black Star process based on the proposed reforming PV inverter. And we know that under a total blackout, a gas generator needs to be started from a still state with the Black Star network side providing the jumpstart power. And this cranking process should be realized by a variable frequency converter driving an auxiliary motor. In the meantime, the synchronous generator is accelerated by the auxiliary motor rotating the attached shaft between them. And also, there is mechanical torque coming from a gas turbine prime mover to drive the synchronous generator. And the black start sequence is as follows. First, we pick up the load on bus 4. The TVL, which is the enabling of GFI control, should be designed short after that. And then energization of a long transmission line between bus 4 and 5. The closing of circuit breakers 3 to pick up load on the bus 5, and then to energize another transmission line. And after that, we should close CB5, which is interconnecting the induction motor into the system. And this is the beginning of the gas generator acceleration and synchronization. And after that, it is to connect the gas generator into the system, which is exactly the time of the TBBS, which is the power Joule mode starts. So we can take a look. This is an example of transmission line energization, which is the closing of circuit breaker 2. And when we are energizing this long transmission line, the propagation of traveling waves can create a large and rapid power surge. And also the shunt reactance will charge. So this process can cause another slower overvoltage transient. And if we take a look of the simulation results measured on the PCC of the inverter, we see that it can withstand the fast power surge. And also it is able to decrease its Q injection to meet the low side demand and the change under the overvoltage dynamic. In the same time, the frequency and voltage can be kept in a range close to the nominal values. Another example is the pickup of a load on the bus 4. And we can take a look of the simulation dynamics on the PCC of the inverter. and the inverter can adjust its power injection to meet the varying grid side load demand, which is increase of the active power demand. And the frequency is able to get back to 60 Hertz under the isochronous mode of the inverter. And also the voltage can be maintained well. And this shows a more detailed implementation for the startup of gas generator. The reason we do this is we're trying to emulating the startup dynamic process of a real gas generator to estimate the impacts. So when the PV inverter starts to provide cranking power to rotate the auxiliary motor along with the SG, and the induction motor has a much smaller power rating compared to the gas generator. And we have a variable frequency drive. It has a back-to-back structure, and the rectifier side is controlled to maintain the DC link voltage. The inverter side, it utilizes a field-oriented control. It allows the regulation and the controlled ramp-up of the motor rotating speed. The mechanical torque imposed on the SG is the summation of a mechanical torque from auxiliary motor and gas turbine. So within the low rotating speed region, below 0.5 per unit, only the auxiliary motor rotates the SG. And when the SG speed reach 0.15, the gas turbine will start the combustion process. The GT torque will kick in, and it is coming from a gas turbine equivalent model based on the gas turbine power speed characteristic curve. And after the idle speed is achieved, the gas turbine enters self-sustaining zone, and the motor can be detached now. The gas turbine will reach full speed. And after that, the IEEE gas turbine model, which is GGOV1, it will kick in. And the synchronization mechanism will detect the phase voltage and the frequency difference on both sides of the circuit breaker 6 and close when the synchronization is reached. So with the presented cranking implementation, we see the synchronized generator, it can be fully successfully accelerated. And the mechanical torque coming from gas turbine and the auxiliary motor. And also, we see the dynamics of the PV inverter. It can produce the additional power required by the variable frequency drive and before the auxiliary motor is detached. It can be noticed that even we need to offer the energy to increase the rotating mass of a large-scale SG, the required additional power injection is quite small compared to the SG power rating of over 100 megawatts. And this means the IBR can jumpstart an SG with much larger power capacity compared to itself. So let's take a final look of the complete simulation results of the black start process. We see that after circuit breaker 6 is closed and the power balance synchronization is enabled, the automatic power sharing between PV and SG can be realized by their PF droop. And the gas turbine governor step up the power reference, so the SG can start to inject active power into the black start network, which will alleviate the under frequency and the over voltage condition, bring the PCC voltage and frequency closer to nominal value. And another thing is we see the frequency and voltage of the system, it can be maintained under all switching actions and all the grid side variation. So this is the concluding remarks. We propose an IEEE 2800 compliant grid forming control. It can operate the inverter-based PV plants as black start units, and it can offer great performances, both in voltage frequency regulation and also a great transient withstanding capability. And also we access the GFI stability under weak grid condition, especially in the initial stage of black start when there is no other target generating unit is cranked. And it can providing possible guideline establishment for the black start inverter control design. And also, we have the simulation results of a complete black start process cranked by the GFI under various switching transient scenarios, including the cranking of a large-scale synchronous generator. And our GFI is able to effectively adjust its P and Q power and generate to keep the frequency and the voltage of the system within an acceptable range. And that is everything I need to cover today for the presentation. Thank you very much, and I'll be happy to answer any questions you guys may have. Thank you very much.
Thank you, Biqi, for this very nice presentation. Okay, so we have a few minutes for Q&As. So if you have any questions or some interesting points stood out to you, please feel free to ask.
Okay, I think I have two questions in regarding to the simulations. The first question is about what is the model you choose to model the grid-forming inverters? Is the detailed switching models or just the average models to study the transient behaviors of the black start process?
For now, we are actually using an average model for the PV inverter to do the simulation. But for the drive, variable frequency drive for the auxiliary motor, we are using a switching model.
Okay, thank you. And also, could you please go back to page 12?
Yes.
Yeah, I have the second questions about that page. Yes, here, this is the test bench system, right?
Yes.
So it's basically a radial structure like 3 nodes connected in series. And my question is, when you are choosing the test bench to study the stability issues and other issues in regarding to black start process, how do you finally come to this kind of system architectures, but not others? For example, a ring structure or even more complex intermeshed structures. So is this IEEE defined standard system, or this is defined in regarding to some other concerns or considerations?
Yes, I probably have mentioned before. So this transmission system, it is part of a real system. So we are working with Dominion Energy for this project, and they provided us with a PSSE model of some real grid and generating units they have. And we extract the data from the PSSE model to this testbed. So we think it can be although the topology is simple, but it can be a good example to show a simple but complete black start process. But as you mentioned, it will also be good and a good choice to use IEEE-based model.
Okay, thank you. And sorry, I forgot to introduce myself. This is Xiaotian Xiang from CPES Arlington Lab. Yeah.
Thank you very much.
Thank you.
All right, thank you for that engaging discussions, and let's thank Biqi again for the nice presentation.